You've all been waiting for this section, applications of matrix operations. Yay! Why are we doing this? There is a reason. So there's a lot of applications. You can do electrical networks, difference equations, stochastic matrices, consumer preference models, cryptography, input output models, and least squares regression analysis. That's a whole lot, right? And you think that's everything? No, there's a whole bunch more. So electrical networks.
You know we can't see that, right?
Nope.
It's really fuzzy.
Let's try again.
I wasn't sure. I was like looking
Nope.
down here.
Appreciate it. There we go. There. Oh, the application, isn't that cool? And then see there they all are. Alright, so electrical networks. Current flow in a simple electrical network can be described by a system of linear equations. And just simple things like voltage is measured in volts with resistance and your current flow. And you can have a whole series of these to represent the system. And then we have difference equations. In many fields like ecology, economics, and engineering, you have a dynamic system that changes over time, so this is a good way to model it. Several features of the system are each measured at discrete time intervals. So you have a sequence of vectors, when it's time 0, time 1, time 2. Okay, and they all provide information about the state of the system at the kth measurement. What time measurement you're doing, you can specify that. And then there's a matrix that you can create. And this is called a linear difference equation or recurrence relation. I think the recurrence relation makes sense because that's based on a time. Given such an equation, you can compute all those unknowns. And an example is a subject of interest to demographers is the movement of populations or group of people from one region to another. So a simple model considers changes of the population of a certain city and its surrounding suburbs. Where's the population moving? Is it moving to the suburbs or the suburbs moving into the city? And at what rate are they doing so? We have stochastic matrices. And many types of applications involve a finite set of states. And if they're considered states, they call those matrices S's. Okay, and like residents of a city may live downtown or in the suburbs, right? So voters may vote Democrat, Republic, or Independent. Soft drinks might buy Coca-Cola, Pepsi, RC, right? Different brands. And each one of those is a different state. So it can be how many populations living in Washington state, how many people are in Idaho state, right? But that state doesn't mean state, it means just an area. So the probability that a member of a population will change from the J state to the ith state is represented by a number. And notice this is greater or equal to 0 or less than or equal to 1. What does that mean? It's like a decimal, right? It's a percent. And if I do percent, what's the biggest I can have for a percent in reality? 100%, right? Or 1. And the lowest percent I can have is 0. Okay, so that's why it's got to be between 0 and 1. And they use p's because it's a probability. So probability of ij equals 0 means that the member is certain not to change from one state to the other. But if it's got a probability of 1, it means it's for sure going to move from one state to the other. Does that make sense? So like, this person is not going to move to the city no matter what you tell them. This person is for sure going to move to the city no matter what you tell them. Right? Just moving from one state to another. And this matrix is called the matrix of transition probabilities because it gives the probabilities of each possible type of transition or change within the population. And it's really important to think of it from to. So what is the likelihood of me going from Ferndale to Bellingham? What's the likelihood of me going from Ferndale to Mount Vernon? Does that make sense? So it's from and to. From some state to some other state. And it always is from and to, okay? And you'll notice that this position is you compare to this one to this one. At each transition, each member in a given state must either stay in that state or change to another. You can't live both in the city and in the suburbs at the same time. Although I kind of think if you're on the border, it's almost like that, but technically there's a city limit, right? You're either one side of the city limit or the other. And this type of matrix is called stochastic, or regarding conjecture. An n by n matrix P is a stochastic matrix when each entry is between 0 and 1, and the sum of all those entries has to be 1. You can't have more than 100%. Okay, so you literally can take all of these percentage, these probabilities, and you add them up together and see if it's less than or equal to 1, or equal or not equal to 1. Does that make sense? Okay. And then we have a consumer preference model. This is kind of cool because we have, in this, notice there's only 3 options in this one, because it can get really confusing, right, when you add a whole lot of options. So to keep it simple, your homework will have just 2 options to start with. You have satellite A, satellite company B, or no satellite. And actually, in reality, how many choices do we have in living in the city? You have 2, a satellite company or no satellite most of the time, right? A lot are for cable, kind of. So what this is showing is if you are currently with company A, this little arrows like this means you are 70% likely to stay with company A. If you have this 20% arrow says if you are with company A, there's a 20% chance that you'll go to company B. If you're at company B, there's a 15% chance that you're going to go switch to A. If you're with A, 10% chance of going to no satellite. If you have no satellite, you're 15% chance of going here. Does this make sense how the picture works? So of course they're going to tell you in words and you have to create this picture. Can you do that? It's not too bad. And then from there you're going to make your stochastic matrix. So remember it's from to. So if I'm with company A, what's the likelihood that I'm going to stay with A? Well, 70%, so 0.7. There's a 20% chance that I'm going to go from A to company B. There's 10% chance that I'm going to go from A to none. If I look at B, the chance that I start at B and end with A is 15%. The chance that I start with B and stay with B is 80. The chance that I start with A and go to none is 5%. Does this make sense? How you take this picture and go here? Now technically, using words you can probably go to this, but I find the picture very helpful. It helps me kind of keep all the things in the right order of where it's going. Okay, so it's from and to. Any questions on that? Okay, so then this is my favorite part of this homework is the cryptography. So it's a message written according to a secret code. And you're going to have to encode and decode message, which I think is totally cool. So the first thing that has to be done, and we take care of this for you, is you assign a number to each letter in the alphabet. So this has already been done for you. Can you do this on your own? Create a whole different numbering system? Absolutely, it's pretty cool. Just don't make the numbers too big or you're gonna hate yourself. You then convert the message to numbers and partition it into uncoded row matrices having n entries. Okay, so if I have meet me Monday, and I want it, and you'll see in your homework you'll be given a matrices, so you'll know how to separate, how many separate, because sometimes we may have a 3x3 matrix or a 2x2. If you have a 3x3, you're going to do 3 letters at a time. If you have a 2x2, 2 letters at a time. Okay? So in this case, what you're going to do is you're going to separate it, and what I do is I just write it and then I put a line in between where I'm separating. And you notice that spaces count. So you gotta remember to keep the spaces in there as part of it. Okay? Kind of cool? And then you'll have to look up, based on your letter assignment, you'll have to write down each number those letters represent. And then to encode a message, you choose a matrix and you multiply the uncoded row matrix on the right to obtain the coded row matrix. So basically, if I can make any 3x3 matrix, any one, it doesn't matter. I can make whatever one I want. I can choose whatever number system I want. And I can take a message and turn it into numbers. And then and decode it going backwards. Is that not kind of cool? And you'll see it's actually very easy. It's just very repetitious. So make sure you guys are looking carefully on your homework, because I don't make you do the whole message. If you want to, you can for fun, because it's kind of fun, but you don't have to. So just make sure that you look on the homework to see how far you need to go on it. This will make more sense when you actually see an example, but it's pretty cool. And then we have Lee and Tiff input-output models. And it's similar to the from-to, only it's user output, supplier input. And it talks about an economic system with a whole bunch of different industries, right? And each industry needs raw materials, and those raw materials can come from itself, or it can come from different suppliers. And that's what these show, is basically a bunch of industries and where they get their materials from. And again, when we get to more examples, it'll make more sense. In producing each unit of output, an industry may use the outputs of other industries or itself. And you let the amount be the output of, and remember the I and J, don't let that confuse you, right? It just is rows and columns, okay? So for an example, if I had D12 was 0.4, well D12 is right here, okay? The user is industry 2. Do you see that? Okay, so this is the industry 2 to produce 1 unit of its product. It must use 0.4 units of industry 1's product. So for industry 2, to make their 1 unit of product, they need 0.4 from industry 1.
So why, I might miss, or why is it 1, 2? Is it, are they doing industry 1 and then?
This is just an example showing you of if this was this one right here, if it was 0.4, what that means.
Right, but the 1 and the 2, is that not the row and the column?
It is the row and the column. Yep. So if it was 2, 2, it'd be right here. And then it would say that industry 1 needs, or sorry, industry 2, for 1 unit needs 0.4 of materials from itself. See, I2 to I2. Okay, so instead of from to, it's the user and the supplier. And it basically is showing how industries use each other's resources and how they're connected. Does that make kind of sense? So let's look at an economic system with 3 industries: electric, water, and coal. So they have to tell you how these relate. So production or output of 1 unit of electricity uses 0.5 of itself, 0.25 of water, and 0.25 of coal. To do water, you need 0.1 electricity, 0.6 of itself and 0 units of coal. To produce coal, you need 0.2 electricity, 0.15 water, and 0.5 of itself. So they're going to give you this information, and from this information, what do you have to do? You've got to create that matrix. So the key is you start with your users, and you have your suppliers, and they're the same, right? But it's the from to kind of scenario again. Okay, so if I'm looking at electricity, it's 0.5 of itself. So 0.5, you see how it's electricity to electricity. And then 0.25 of water. Here's my electricity, but 0.25 water. And notice, what does this column add up to? 1. Does this column add up to 1? No. Okay, it's not the same as the stochastic model. All right. Okay. Does that make sense to you guys? Can you replicate? All right. And then we're going to do least squares regression analysis. And this is what we do in statistics to develop linear models. When my undergrad's in industrial engineering, I had a whole quarter on this. So it's used, below we're going to look at a visual demonstration of this. Okay, so here you have data, right? And then there's a line that kind of represents that data. You want to figure out how well does that line represent it. And what you do is you do the difference of values between what you want it to be and what it is. Okay, so you square the difference and sum the results, and you obtain a measure of error called the sum of squared error. And it looks something like that. Okay, is this enjoyable to do? Well, it is if you just use a computer, right? Then we have the least squares regression analysis. And notice it's kind of interesting because you have the transpose of x times x, and then what? It's inverse. And then you've got the transpose of x times y. And is any of those individual pieces particularly difficult? No, but when you put them all together, is it fun? Yeah, not so much. Okay, so you're going to find x, and what's interesting with this is you have ones in the first column, okay? So you're going to be given x, y's, a whole bunch of points. And the ones go with the x's. And then your y's are your y. And then you're going to find the transpose of x, and you're going to multiply it by x, and you're going to take the transpose of x and multiply it by y. And then you have to find the inverse. Now, if you look online, I did the inverse the hard way. If it's a 2 by 2 matrix, is there an easier way to do it? Yes. Why did I not do it at home? Well, at the time, it was something I had to memorize, and I don't like memorizing things, and I knew I could do it perfectly well the other way, and it helped me reiterate all the good stuff that I've done before. Here's the thing I know now. You're going to have to do that in the future, so might as well use it now. So if it's a 2 by 2 matrix, use the easy way. It's okay, I give you permission. If you don't want to remember it, and it's kind of a pain, because remember it's really confusing, you switch 2 and you change the signs of the other 2, and then you have a fraction that you have to multiply by. If you don't want to memorize it, you don't have to. All you do is take that matrix, multiply it by the identity matrix, and then simplify it until you have the identity matrix times the inverse. Okay, both ways work. And I did the hard way, but tonight I'll do the easy way for you, okay? So you'll have examples of both. Okay, and I think finding that inverse was the worst part. And then what happens magically is you're going to take all this, and you are actually going to end up with a 2 by 1 matrix. And then you have to know what these matrices mean when you solve them, right? Like, what is this telling you? Well, this is telling you that you're B, and this is your M. What does the B and the M refer to? Y equals mx plus b. It's the equation of a line. So taking this matrix you can then say y equals what? And that will be the equation of the line that best matches your data. Kinda cool, a little bit. Not my favorite problem to do, but kinda cool. Questions on that? Oh, again, will make more sense when we do example. Okay, so shall we do some problems?